LTN Global. I'm part of the team that does encoders, decoders, and transcoders. So basically ingesting uncompressed video, compressing it, transporting it, decoding it as needed. So I think that a lot of the people in this audience who do play with video, it's mostly in the compressed space already, where you're doing things like HLS segmenting, or you're trying to transcode streams for delivery to multiple sources. And, you're typically playing with, these sorts of parameters: codec, resolution, bit rate, GOP intervals, segment sizes, et cetera. So we're not gonna talk about any of that. Instead, we're gonna be talking about this other part here, where before you do feed it off to the codec, you might need to do stuff to it. You might need to deinterlace it. You might need to scale it. You might need to change the frame rate if you're going from one region to another, US to Europe or what have you. And all these things can really screw up the video. So, really what we want to talk about is where some of this stuff can go wrong, where there are some of the gotchas, and basically give an introduction to the terminology. So at least when you're setting up your transcoder, you know what some of these knobs and dials do. So let's take a step back to the basics for a minute. Let's talk about what raw video is. If we think about video in the raw space, we've got pixels. These are built-up components of Y, U, and V. And if you look at this very nice little picture here, you can see that this is the real image, Y, U, and V. And they're organized in that manner so that to aid in compression, because compression is good. Also, there are cases where these may not be at the same proportion. You may not have one element of luma to one element of chroma. You could play with these parameters to, to optimize. So, and that's sort of where we get to what's called chroma subsampling. And we'll talk about that more in the next slide in a little more detail. But, the big things to bear in mind is that, typically these pixels can be arranged in a packed format where the luma and the chroma samples are adjacent to each other, or they can be in planar format where you have all the luma and then all the chroma. And these are things that aid in compression, that aid in the way that you, get lower bit rates. So it's also important to note that, why do I care? Isn't everything just in 420, planar? Well, not necessarily. And in fact, the converting between different formats could introduce loss in quality. It could be expensive on your CPU. It could affect how well you scale. So if you're trying to do lots of transcoding, you kind of care about whether or not these things are happening. And this quick little grep here, there's 270 different pixel formats in FFmpeg, and which is basically the Swiss Army knife and kitchen sink of pixel manipulation. There's a lot of different formats, and they don't all convert to each other cleanly. They don't even all convert to each other without loss, and they don't all convert to each other with the same performance profile. And so these are all things to bear in mind when you look at any sort of raw video transformation. And so let's talk a little bit about pixel layout and how some of this stuff is organized. And this is important in a few minutes, but basically there are two big formats you find for pixel layout. One is 420, which is what you see pretty much everywhere in consumer, where you've got for every basically the chroma is shared by adjacent pixels, both horizontally and vertically in pairs. And then you've got 422, which is basically on a per row basis, you're sharing your chroma and luma samples, where you have one chroma sample per every 2 luma samples. And so really what you find is that in the consumer space, everything's in 420. In the professional space, everything's in 422. And in particular, when you start talking about things like SDI, digital video, 422 becomes really important. And all this impacts your quality, because when you want to do transforms on this data, for example, rotation, scaling, deinterlacing, the fact that you're sharing this chroma information by these adjacent pixels has a quality impact. Now you can say, well, why do we bother with that at all? I'm like, why do we have why are we sharing chroma? Why isn't it 1-to-1? And, you know, the reason for that is that the human eye is more sensitive to changes in brightness, which is what luma is, versus color. And so if the color is, you know, if the color quality is slightly off, you're less likely to notice than if the quality of the brightness is off. And so most of these algorithms cater to that when they decide how to divvy up the bits for, you know, when they want to do compression. The other thing is that this uses a lot less memory than this does. And, you know, we talk about 1080p 60, you know, 1920 by 1080p, you know, 60 frames a second, you're talking about 3 gigabits of data per second. You know, you're talking about a little around 400 megabytes of pixels. And so now all of a sudden it's like, okay, even for modern processors, that's a lot of pixels to be manipulating. And if you have to do any sort of, whether it's copying, whether it is overlays, whether it is scaling, those are things that impact your ability to do it efficiently. Yeah, can everybody agree that 400 megabytes a second is a lot for stuff going on inside of a CPU? You know, so it's, I mean, I know that, you know, we're all typically operating in the compressed space where it's like, oh, 10 megabits, 15 megabits. Well, that's like 2.5, 4 megabytes per second, give or take. This is 400. So now all of a sudden you start to care about how much space does each pixel take. These are very conveniently from Wikipedia because I am lazy. So pixel depth. Yeah, so there are 2 basic pixel depths that we find. There's 8-bit and there's 10-bit. Much like the 422 and 420, 8-bit is pretty universal in consumer grade, TVs, et cetera, ATSC over-the-air transmission, streaming, et cetera. 10-bit is increasing in popularity, and that's basically what's universally used in the broadcast industry, further up the production chain. Most cases, all production happens in 10-bit. All your SDI links and all your routing gear, all this stuff that happens in the raw space is in 10-bit. And then at the last mile, it gets converted to 8-bit before it gets put out. ATSC 3.0, which if anybody's heard of that, that's the new over-the-air transmission standard. They're moving to 10-bit. They're recommending it, basically HEVC 10-bit with HDR. We'll talk about HDR later. So, you know, again, you know, why do we care? Well, you know, it's not just more, it's just not another 25% worth of bits. You know, some of this comes down to things like alignment. It's really easy to shuffle stuff around in 8-bit or 32-bit blocks where everything's 8-bit aligned. Shuffling around bytes, or, you know, shuffling around data in 10-bit blocks, it's a lot harder. You know, when you talk about things like optimized assembly, when you want to do things efficiently, you know, you either have to store that in a 16-bit register. You know, these are things that it's just a lot easier to do this stuff in 8-bit. As somebody who's like written low-level assembly code and it's like, oh crap, you know, I have to like transform it into 16-bit before I can manipulate, then go back to 10-bit, and you know, playing with byte packing routines and stuff like that. It's a pain in the neck. 8-bit is nice. Everything aligns on an 8-bit boundary, much easier. Aspect ratio, we're going to talk about briefly because we were talking about pixels. You know, most of us are in computer land. You know, we think of our monitors, you know, 640 by 480, 1024 by 768, whatever they use nowadays. But the big thing that as computer users we mostly think about is we assume the pixels are square, because why wouldn't they be? Unfortunately, they're not always square, you know, in digital video. And a lot of this comes back to the days of standard definition, you know, old-fashioned analog television. They wanted to play a lot of games and a lot of tricks to do it efficiently. And one of the things they ended up doing was basically coming up with pixels that weren't square, where the actual ratio of the pixel is rectangular. And that caused all sorts of headaches and still does to this day if you have to do any work with standard definition video, even if that means converting it to high definition video. But you know, you end up with all these wacky things relating to the aspect ratio of the display, the aspect ratio of the pixels, the aspect ratio of the pixel, which is just another word for the aspect ratio of the display, and the pixel aspect ratio. And unfortunately, somebody decided to use this terminology, recognizing that, oh, if I say PAR, do I mean the picture or do I mean pixels? and it causes lots of confusion, and everybody hates it, but, don't blame me. But anyway, so when we talk about aspect ratio, though, typically it can be signaled in a number of different methods, depending on what your transport is, whether it's SDI, whether it's H.264, whether it's MPEG-2. There's a whole lot of vintage stuff out there. This thing, WSS, is widescreen signaling. That's what they were doing in Europe when they decided they wanted to do widescreen video, but use old-fashioned standard definition decoders without actually changing anything. They're like, oh, we'll just send an extra bit that says, take this 4:3 video and stretch it to 16:9. AFD is in the same vein, but we have to do it different in the US just because. Video index, don't care about that. Bar data, don't care about that. The point is, though, these decisions about aspect ratio impact how you're actually what you need to do to your video in order to properly preserve aspect ratio, and you end up with really wonky FFmpeg command lines that in order to accomplish some of this stuff. The other big thing about aspect ratio is that it changes over time, or can change over time. You're watching 16:9 video, and then you go to a commercial, and the commercial's in 4:3. Or much more common, you're watching 4:3 video because it's old, like Westerns, and then it goes to commercial, and it's now 16:9. And so these are not properties of the stream that you could just look at the first few frames of video and say, oh, this is 16:9 video. I'll just use that the entire time. You actually have to be looking at it on a frame-by-frame basis and potentially changing your pipeline to take that into account. The other thing about aspect ratio, letterboxes and pillar boxes. Everybody knows what letterboxing is because you've all watched DVDs in the last 20 years. Pillar boxing is the exact opposite, where you take 4:3 video and you show it on a 16:9 TV, and you've got black bars on the left and right. Interlaced video. God, we hate interlaced video. Why could we not get rid of that? The answer is because people still want to watch stuff that was made before 1995. So basically what we have is all this legacy stuff. And oh, by the way, when I say legacy, I mean even over-the-air television. Most of it is interlaced. If it's 1080i, there are basically only 3 formats that you find in the United States for over-the-air television: 1080i, 720p, and 480i. 2 out of 3 of those are interlaced. So unfortunately, you have to deal with this stuff. And even if that means I want to take this TV and I want to convert it so I can make it available for over-the-top, which, by the way, fortunately, almost nobody in over-the-top supports interlaced. They all said, forget you, convert to progressive, and then, we don't have to worry about it. The downside is if your job happens to be taking interlaced content and making it available for over-the-top services or for YouTube type services, you're going to have to do the work to de-interlace it. This little diagram here kind of talks about how interlaced video is composed of the top field and the bottom field. Every other line. This is all legacy having to do with how CRTs used to work. Remember those before we had flat panel TVs? The key thing to bear in mind here is that, oh, you just take this and this and combine them together and you get the picture. Wrong. So the issue is these are actually from 2 different moments in time. While it's not just, oh, these are the top fields and this is the top field and this is the bottom field. This is actually from time 0 and this is from time 16 milliseconds. And so this has all sorts of fun effects when you can't just combine them, because if you have movement, you'll actually see combing effects. And that's where, you have to do de-interlacing. It's not just, can I take these 2, areas of video and stick them together and send them along their way? You actually have to take into account that, they're from different periods of time. So that's sort of, we get to de-interlacing. A few different strategies. I'm not sure anybody cares about this, but basically they come down to either throwing away half the data and scaling it up vertically. There are strategies that blend the 2 fields together in some form. And then you have hybrid strategies where you actually try to compute motion vectors and use that to drive which of those 2 strategies you use on a per frame basis. So you can say, oh, there's movement in this part of the frame, therefore we want to do line doubling, whereas over here there's not movement and therefore it's okay just to to extend the field. So these solutions, they sort of work. They work pretty good. As TVs get bigger, when they don't work well, it's more obvious. Anybody who tries to watch the Golden Girls on their 52-inch TV, it looks terrible. And a lot of that's because of interlace effects, because they get magnified as you're now trying to represent, each 480i line that was in that original standard def video is now 8 lines tall. Now all of a sudden interlace effects are much more obvious. The other thing we're mentioning here, and not to beat on FFmpeg or some other tools, a lot of video processing tools don't know about fields, or they don't treat them separately. What they do is they just kind of compact them together into a frame, which is okay as long as you indicate along the line that this is interlaced content, and in particular whether or not temporally the top part came first or the bottom part, because eventually you're going to have to do stuff to it and you need to know which part in time occurred first. FFmpeg is terrible at this, and I've got a bunch of patches and I've been yelling at them to try to get them merged. It's not going well. But the point is that there are all sorts of weird edge cases where the video can look like garbage because either the state of interlace gets lost, or the notion of which part of it occurs earlier in time doesn't get properly handled. So, why do we care about interlacing? Well, because people want to read this. Like the instances where interlacing artifacts become most obvious are anything that's moving. And the test case I always like to use is TV program with the ticker. If you actually had to read this, it would be very difficult to read, especially if it's scrolling across the bottom as it always does. The text is not particularly tall, and there's a lot of variation, obviously, between black and white. So it's really bad trying to read that without properly deinterlacing it. Scaling. So why do you want to scale video? Well, you want to scale video because the video you're getting from your user is 720p, and you need to deliver it as 5 different renditions to your end user at different bit rates, and say, okay, I need to give 720p, and I need to do 320 by 240, and I need to do 640 by 480, and I need to provide these different variants of it. And oh, by the way, they've got a 4K television as well, so we need to upscale it too. There are lots, like with the deinterlacing, there are lots of different ways to do it. If you look at the man pages for SW scale or for the VF scale filter in FFmpeg, you'll see a Chinese menu of different scaling algorithms and heuristics to use. They vary in quality, they vary in how much CPU it takes to do them, and figuring out which one is appropriate for the type of content you have is really hard. Again, then another fun reminder about aspect ratio. The scaler is sort of agnostic to aspect ratio. So if you're taking in 720 by 480, because that's your standard definition video, and you want to turn it into 1080i video or 1080p, you need to preserve the aspect ratio, or else it's going to get squished. And then finally, interlace chroma subsampling, which is a sort of a weird edge case, but scalers are lousy at this. This is what it's supposed to look like. This is what it looks like with FFmpeg if you don't properly set the interlace flag, because it doesn't understand that the chroma sampling, the arrangement of the chroma pixels is specific to interlace. It's actually shared across different alternating lines. It's pretty easy to say that looks bad. And in fact, this actually happened at a customer where, like, I'm looking at this video and it's like, oh yeah, I understand why they're complaining. Frame rate conversion. Why do you need to do frame rate conversion? Well, because the video you're getting is at 60p and you want to deliver 30p, or it's made in the US and it's at 60p and you want to deliver it to Europe at 25p. Two basic scenarios for frame rate conversion: 30 to 60 and 60 to 30. Those are pretty easy because you're basically either throwing away frames or duplicating frames. When you want to talk about going from US formats to European formats, it gets a lot harder because it's not an even divisor. Going from 30 to 25 or 25 to 30 means you can't just throw away every other frame. You have to decide which frames to throw away. And in some cases, you may need to blend them together to provide a smooth experience. Again, easily visible with stuff like a stock ticker, where you don't want it to be stuttering because it's not moving at a constant rate. Different algorithms for doing that: dropping and repeating frames, linear interpolation, motion adaptive. Not sure how much, you could Wikipedia those and understand the differences. For time, I don't think we're going to go into that. I will tell you, let's share a little anecdote about how they don't always work the way they're supposed to do. So I was doing some of the horse racing. I had a very high profile customer. We were picking up video from a very popular horse race and delivering it to Europe. And so we had to go from 1080i 59 interlaced to 720p 50. So we have to deinterlace it, we have to scale it, and we have to frame rate convert it. And so we went out and bought a $10,000 piece of hardware, and that horse race looked great. Okay, we were very happy watching the race, watching the horses go around, looks good, picture's nice and smooth. And then it goes to the scores at the end where it shows the results. And there's like visual flickering and, the actual, the bars. And this is just stationary video. This is the results, the score. And it looks bad. And you think, oh, well, it's just the score, except it turns out the people with the money, that's all they care about. And so if that doesn't look good, it was a showstopper. One other thing about frame rate conversion, captions, closed captioning, that thing that the FCC requires us all to do, is often carried along with the video, and tied to the actual video frames. And so if you frame rate convert, you may lose half your caption data. And if you've ever, seen the captions go across where it's HLOWRD instead of hello world, that's because basically you threw away half the frames of video without actually redoing your captions, which, by the way, is what FFmpeg does. One other thing about frame rate conversion and frame rates in general, we talk about 60 FPS in the US. It's usually 59.94 FPS. There's a really long and complicated reason for why that is, and goes back 50 years. Do not treat them as the same thing. Otherwise, you'll get 10 minutes into your program, and the lips won't match the voices, won't match the audio anymore. So just something to think about if you're doing a frame rate conversion. People are really sensitive to AV synchronization. If it's off by more, they say the number is like 3 frames, which is like 90 milliseconds. If you're more than 90 milliseconds out, people will complain. I have firsthand experience with this because I built myself a DVR at my home, and my wife wouldn't watch TV because you should watch The Office and the mouths weren't in sync with the audio. And so it was bad. Anyway, so something to think about. Color space conversion. We like to think that if we're converting video, we just need to scale it down, change the frame rate, and we're done. Except that's not quite true because the definition of color is not static. If we look here, this is what we took for HD. This is the entire range of color that's possible. This is what can actually be done by in HD video. And so where this becomes relevant is, when your advertisers say, in my commercial, does Coca-Cola red look correct? They're sensitive to that sort of thing. And so, the big thing with the new HDR stuff that everybody's hearing about is that now you can represent more of the color. Okay, that's great. Good stuff. The challenge there, of course, is that, if you want to convert video from one format to another, you can't just scale it and frame rate convert it. You may actually have to change the color space as well, which involves a lot of math, and it's really expensive. And fortunately, Ronald, who is not here today, the David guy, actually wrote a really nice FFmpeg filter that does that. So thanks, Ronald. So it wouldn't be talk about video without talking about HDR, because that's what everybody in the industry talks about, how great HDR is and how everything's moving to HDR and all your 4K TVs support it. And HDR is all about having a wider range of brightness. This is really important for cases where you're doing gaming footage and you want to be able to see that darkened guy in the corner shooting at you. The ability to actually represent brighter whites and darker darks, as well as wide color gamut, which is what we talked about before, being able to reproduce the color more faithfully. You could spend an hour talking about HDR. We're not going to. One thing worth noting, though, is that if you're blending graphics into your video, blending white, RGB 255, 255, 255 does not work in HDR because it will burn a hole in your eyes because it will be maximum brightness. So you need to take that into account. Yeah. So we'll talk briefly about tools and how we do some video evaluation. I'm sure everybody's seen this picture before. And it's like, well, what the hell is this? These are color bars. And this is not a random assortment of colors. It actually has a very specific engineering purpose when calibrating video systems. And if you look over here, this is your Luma representation of this. And you can actually see there's a staircase and there are discrete levels. And if these levels aren't correct, you can make adjustments and see that your video is not properly formatted. Over in the chroma space, same thing. This is an IQ representation of color. How many of you remember TVs? They had that knob called hue. That's where this comes into play. If your hue is wrong, this whole thing will be rotated, and the people's faces will be purple. So this is these tools are typically used in your production system to actually verify that the levels are correct, both in the Luma space and the chroma space. There are specifications that define these things. And in fact, if you look at an analyzer, you can actually see what the actual YUV values are and compare them to the spec. And since this is the simplest thing in the world you could possibly encode, it should be spot on. You'd be surprised how often it isn't. So this is a really, really expensive test pattern that I'm showing you a screenshot of because it actually moves. That lets you look at all sorts of properties of video. This comes with a roughly $10,000 piece of equipment in order to generate intellectual property. But the point behind this is a lot of stuff going on here, and each one of these regions has a discrete way that you're supposed to examine it to see if your 10-bit video got decimated to 10-bit, or if your chroma subsampling is screwed up, or your fields are inverted, all sorts of stuff like that. We're going to move a little faster. Sorry, Eric. Me too. One thing worth noting here is, we're not, this is not a copy of Playboy. The reason for the pictures of the models is because one thing that humans are really good at is noticing that, skin tones are off. And so even within this pattern, they have some real people up there. So you can see that, oh, it's a little too green. It's a little too red, and you can adjust accordingly. If you look at the documentation, it'll actually tell you what every one of these values is supposed to be for 10 grand. This is an aspect ratio card. Pretty simple. The whole point of this, though, is to make sure the circle stays as a circle. If the circle turns into an oval, you've screwed something up. That often happens when you're scaling video. It happens a lot. All sorts of other test patterns. We won't go into what all these are, but there's lots of them. And if you actually care about digital video, you should look these up. These are actually ones that come with a $300 generator that you can buy at B&H, and yeah. And then don't forget about sticking two 42-inch televisions next to each other and just seeing what happened to the picture as a result of your changes. This is my lab. So this is a subset of my lab. It's actually, the whole point of this was actually to measure latency in this case. But I assure you there are 4 televisions there, and you could actually do side-by-side comparison of the original video with the thing that you've transformed, and you can see that, oh yeah, I screwed that up. So we're gonna talk about a few things that can go wrong. This is called the postage stamp effect. You'll notice that this is not meant to be a picture frame. This is actually what happens when you screw up your aspect ratio processing. This actually should be scaled to fill the entire screen. This is actually 4:3 video originally. They had letterboxing, but didn't properly signal it. So it got treated as 4:3 video, and then the TV decided to add in pillow bars. So you end up with this, a whole bunch of wasted space around the edges. I actually saw this at the hotel I was at a few weeks ago. I was like, oh wow, that's dumb. This is incorrect aspect ratio. You'll notice here that this is old television. I've grayed out the logo to, not shame the customer who gave it to me, or is giving it to me right now. But the point being that this is supposed to be 4:3 television, but the decoder doesn't know that, and so it thinks it's 16:9, and so it's actually adding pillow bars to it, even though it doesn't need them. And as a result, everything is horizontally squished. This is a fun one. Yeah, I didn't indicate who this is either, so that's good. This is HD television. It was 1920 by 1080, 1080i video, but clearly it came from standard definition television. And I could tell that because these dots right here are the closed captions. This is, this is called a VBI run-in, and it's actually a little waveform that appears in the first couple of lines in the video. And the irony is that this TV program was produced in 2017. So the content itself originated in HD. It got put out as standard def, and then they scaled it up to high def again before delivering it to us, and then didn't bother to like take into account the captions. So yeah. Anyway, couple thanks. Derek, who's on the video dev channel all the time. He looked at these slides to make sure they weren't crazy. And LTN for, well, letting me make these slides this morning instead of doing customer stuff. Like my friend from Fastly, we are hiring. If you like video, if you know about encoding, decoding, transcoding, if you do TS analysis, if you like to drink from a 10 gigabit fire hose of video, we're hiring. So